Welcome to our second video in this series of videos for our 7th class time series of instructional lecture videos. We ended the first video by attempting a problem of trying to draw a chair conformation for cis 1,4-dimethyl cyclohexane. And we saw that in a chair conformation, one of the methyl groups was axial and the other methyl group was equatorial. I wanted to go ahead and show people with a molecular model system that this is not crazy. This molecular modeling system sort of approximates what that six-membered bond line diagram expresses, with the two methyl groups on the same side of the plane formed by our six-membered ring, and I've straightened the 6 carbons in the ring out to be in a plane. And you can clearly see the two methyl groups are pointing up on the same side of that plane formed by that 6-membered ring. Of course, I have to put this in a chair conformation, so I'll go ahead and do that. Now I think students can clearly see that this is in a chair conformation. And at our 1 carbon, we have this methyl group pointing straight up in an axial position. And then at the 4 carbon, relative to it, we have this methyl group, and it's not in an axial position, it's in the equatorial position. So I hope this helps visualize that part where we ended our first video. And we will continue on with our discussion of chair cyclohexane. So, in our next page of notes, we have this. During a ring flip from one chair conformation to another, so these cyclohexane chair conformers actually flip conformations. Believe it or not, all axial substituents become equatorial and vice versa. And so what I've done on this particular chair conformation is I've drawn all the hydrogens that are equatorial to possess a little red dot. And then we say, oh, there is a ring flip, which happens through a series of steps. And we notice that all the hydrogens that with the red dots that were formerly equatorial, all equatorial, are now all axial. And so I know you might not believe me that this actually happens. But before we consider an energy versus conformation diagram for this process, I thought I would show you with another molecular model. And so we can see that this is a chair conformation of cyclohexane. We can quite clearly see the chair, and you'll notice that all the bonds to the equatorial hydrogens in this chair conformation are green, and all the bonds to the axial hydrogens in this particular chair conformation are white. Now you notice how this is the head of our chair and this is the foot of our lounge chair, which we should all be appreciating in the summer by the pool in Arizona. We know that a lot of lounge chairs can flip, so the head becomes the foot and the foot becomes the head. And so I'll go ahead and do that. This bends down, this bends up. And so if I've done that correctly, oh wow, now I'm at the other chair conformation, and you can see all the hydrogens that had formerly been equatorial with the green bonds, now they are all axial with green bonds. And all the hydrogens that had formerly been axial with white bonds to carbon, they now appear to be equatorial. So we'll go ahead and consider the process by which we convert from one conformation, one chair conformer, to another. Of course, if you have a model set, you can do this, hopefully not all night to your roommate's consternation. But yeah, let's go ahead and take a look at the individual conformations we might reach through the process. So we start out at a chair conformation. We start bringing one end of that chair up such that it becomes planar. If we continue moving that end up from this half chair conformation, we get something called a twist boat. Now the twist boat can go to the boat conformation. It's just puckered a little bit. You could easily probably assume these individual stopping points along the spectrum of different conformations as you flip between conformers with the molecular model. The boat is something, of course, the name indicates it kind of looks like a boat. Well, it does. And of course, from the boat conformation, we go to the other twist boat, and then we continue bringing the left hand side down to the half chair. And if we continue on our way down with the left hand side, we get to the other chair conformation. Now, these different conformations have different energies. Of course, the chair conformations are our low energy points along this process. But let's go ahead and look at what those different conformations resemble in terms of their energies along the way. So here we are with an energy versus reaction coordinate diagram. We start out at a chair. Going up to the half chair conformation, that's 10.8 kcals per mole higher than our chair conformation. We could fall down to a twist boat, that's about 5.5 kcals per mole higher than the chair. And then of course we could proceed through the boat, which is an additional 1.4 kcals per mole higher than the twist boat, so a total of 6.9 kcals per mole higher than the chair conformation itself. It could fall down to the other twist boat, which is of equal energy to the other twist boat on our diagram, and then we could go up to the other half chair, which is of equal energy to the other half chair, and all the way back down to the other chair conformation, which should be of equal energy to the chair conformation that we started out with. So a ring flip or chair interconversion converts all the axial substituents to equatorial and vice versa. We saw that with hydrogens, but it also works with other groups. For cyclohexane, the activation energy is approximately 10.8 kcals per mole. That's the highest energy in converting from the chair to the half chair. At room temperature, a cyclohexane ring will interconvert about 100,000 times per second. If I tried to do that with the plastic molecular model, and I were able to, first of all, muster that energy, the plastic and my fingers would probably burn up in the atmosphere. Alright, that's my feeble attempt at humor. This video has gone on almost 9 minutes. That's probably long enough in terms of holding attention. So I will see you in the next video where we'll study what happens in terms of evaluating different chair conformations with different non-hydrogen groups on them.